For a classification problem where the data comes from only two classes, it's going to be enough to consider just one discriminant function. This is also shown in this figure, and I also want to write it here. The discriminant function in this case is going to be a function g of x of the form w1 x1 plus, and this is going to be a sum over all the dimensions. In this figure I only have two dimensions, and I'm going to keep up with this, but in general it's going to be a sum over all the dimensions plus the free term. And the discriminant can also be written as w transposed times x plus w0. And this w is a d-dimensional vector, and it's a so-called weight vector. And the way this discriminant function works is that it's helping us to do a classification with the following decision. So classification decision. We will take a look at g of x, and we are going to choose C1 if this discriminant, so choose for point x, so choose for x C1 if g of x is larger than 0, and choose C2 otherwise. The set of points where g of x is equal to 0 is a hyperplane. So in general it's going to be a d-1 dimensional subspace in the d-dimensional space of our input data set. And this hyperplane is dividing the input space into two half spaces. And we can see it in this figure in this way. This is the hyperplane defined by g of x equal to 0, and we have one half of our, in our case, two-dimensional space, and this is the second half. And the point is that on this half, the discriminant g of x is going to take positive values, and on this half is going to take negative values. So our classification decision can also be interpreted like this. We take the hyperplane defined by our discriminant function being equal to 0, and on one side of this hyperplane, all the data points falling into that half space are going to be classified as being into C1, and all the data points falling into the negative half space are going to be classified as belonging to C2. One point I want to make is also about W0, what's the significance of W0, and I'm going to make this point in the following way. If we take a look at the origin, g of 0 is, according to the definition of our discriminant, is w transposed times 0 plus w0. And so this is obviously equal to w0. So there are three possibilities. If w0 happens to be 0, then our hyperplane defined by the discriminant function goes via the origin. If w0 is smaller than 0, just like we have in this particular example we have on this slide, then the origin is going to fall on the negative side of our hyperplane. And finally, if w0 is larger than 0, then the origin is going to fall onto the positive side of our hyperplane, meaning that the discriminant is going to be, in our example, somewhere on this side of the origin. I want to open up a little bit more the geometry of this binary classification problem and discuss even more about the significance of this hyperplane that we define in this case. So here are a few points I want to make about this. Let me just reproduce on this slide the figure we had on the previous one. This is x1 and x2. And we had this hyperplane defined by g of x is equal to w transposed x plus w0 being equal to 0. So all the data points x on this hyperplane have the property that g of x is equal to 0. And this w was the weight vector, and in particular this is a d-dimensional vector. And you can also think about this d-dimensional vector as actually being a vector in this space, or if you like, we can also see it in this way, that w is represented by a point in our space. And I'm going to just show it like this. This is, you can interpret this d-dimensional vector as being this one from here to here. So in some sense is defined by this point here in the d-dimensional space. Now, there is an advantage when you interpret it like this, and that is that this hyperplane we've defined through the discriminator, all of a sudden it becomes clear, just because it's of this form w transposed x plus w0, all of a sudden it becomes clear that is the orthogonal, it's an orthogonal hyperplane to w, or if you want in the other way, w is orthogonal to this hyperplane. And when we think about this, you realize that for the orthogonality part of the definition of our hyperplane, the norm of w doesn't even matter. The only thing that matters is the direction. So once we have the direction fixed, then we have the orientation of this hyperplane fixed. So that's also the reason why very often this vector w is chosen to be of norm 1. And the other thing I want to discuss is about this w0, and I'm going to do it like this. If I just prolong this w so that it reaches the hyperplane, and I'm going to focus on this particular point here, which is at the intersection of the extension of our vector w and the hyperplane defined by g of x equals to 0. So this point right here is going to be, obviously because it's on the direction of w, is going to be of the form, if I take this vector right here, so this is going to be of the form r times w, where r is a real number. And this is simply because it's on the direction of vector w. And on the other hand, because it's on the hyperplane, we have that g of rw has to be equal to 0. And when I'm replacing rw in the expression of g of x, we get right away that w transpose times r times w plus w0 equals 0. And so we rewrite this as r times the norm of w plus w0 is equal to 0. And what this means is that we have r equal to minus w0 over the norm of w. And as I said, we can also assume that the norm of w is equal to 1 without loss of generality. So what this means is that the distance of the hyperplane from the origin is essentially given by w0, whether it's normalized by the norm of w or whether this is chosen as being equal to 1. So just to sum up about the geometry of this binary classification, we have a discriminant which is of the form g of x is equal to w transposed x plus w0. And we have a decision procedure by thinking about whether g of x is larger than 0 and is going to be larger than 0 on one side of this hyperplane, or whether it's smaller than 0 and that's going to be the case on the other side of the hyperplane. So this hyperplane is going to divide our space into two parts, one where we describe all the points as, or we classify all the points as being in class C1, and the other one as being in class C2. And this discriminant function is essentially described by a vector W that can be chosen with norm 1, and the discriminant is going to be a hyperplane orthogonal to W and at distance W0 from the origin.